When calculating volumes of spheres or cones, Cartesian coordinates become mathematically messy. Spherical coordinates offer a more natural way to describe curved geometries, simplifying our integrals and allowing us to solve complex physics and engineering problems with much greater ease. Notice how the Cartesian boundaries involve complicated square root functions. By switching to spherical coordinates, we can often transform these difficult boundaries into constant limits of integration, making the calculus straightforward and significantly reducing the risk of calculation errors. We define a point using three parameters: ρ, the radial distance from the origin; phi, the polar angle measured down from the positive z-axis; and theta, the azimuthal angle measured from the x-axis in the xy plane. To cover all space, ρ goes from 0 to infinity. Phi ranges from 0 to pi, covering the north to south poles. Theta ranges from 0 to 2 pi, completing a full rotation around the z-axis. These constraints define our standard spherical system. To integrate, we need the volume of an infinitesimal element, dv. Because the grid lines are curved, the sides of our box are not just d-ρ, d-phi, and d-theta. We must account for the increasing width as we move away from the origin. The general setup involves nested integrals. We typically integrate with respect to ρ first, then phi, and finally theta. The order can be changed, but keeping the Jacobian factor next to the differentials is standard practice for clarity. Let's calculate the volume of a sphere with radius r. Our limits are simple: ρ goes from 0 to r, phi covers the full vertical arc from 0 to pi, and theta covers the full rotation from 0 to 2 pi. First, we integrate ρ squared with respect to ρ. This gives us ρ cubed over 3. Evaluating from 0 to r, we simply get r cubed over 3. This constant can now be moved outside the remaining inner integrals. Next, we integrate sin phi with respect to phi. The antiderivative is negative cosine phi. Evaluating from 0 to pi, we get -1 minus -1, which simplifies to exactly 2. We are almost there. Finally, we integrate with respect to theta from 0 to 2 pi, which simply gives us 2 pi. Multiplying everything together, r cubed over 3 times 2 times 2 pi results in the classic formula, 4/3 pi r cubed. What if we only want the volume of the upper hemisphere? The only change is the limit for phi. Instead of going all the way to pi, we stop at the equator, which is phi equals pi over 2. Consider a cone topped by a spherical cap. Here, ρ is limited by the radius of the cap, and phi is restricted by the angle of the cone. This demonstrates how spherical coordinates describe slanted surfaces perfectly. Integration is essentially the process of summing up an infinite number of these tiny dv elements. By defining the boundaries correctly, we ensure every part of the 3D shape is accounted for exactly once. To summarize, always identify your radial and angular limits first. Second, set up your triple integral, ensuring the ρ squared sin phi term is included. Finally, perform the nested integration starting from the innermost variable. Let's test your understanding. If phi starts at the positive z-axis, what is its value when it reaches the horizontal xy plane, also known as the equator? Think about the angle between the vertical axis and the horizontal plane. The correct answer is pi over 2. Since phi measures the angle down from the North Pole, a 90-degree drop lands exactly on the equator. Thank you for exploring spherical integration today. Generated by Vision Solve AI.